Okay, so this is for us to go through the thermal properties of metal tutorial. Okay, the answers will be uploaded. It's just that when it comes to the calculation question, there are a long strings of numbers and equations and all that. Okay, but some of you make mistakes. Why? Because to me, I attributed it to you guys not knowing whether is there a change in state or is there a change in temperature. So how do we ascertain whether is there change in state or change in temperature? It must be from the question itself. That means you must be able to interpret. Okay? And even after you are able to interpret, you also need to draw what is important, which is your cooling and heating curve. Okay, so this is in your definition. I will not go through, yeah. I will upload on Google Classroom. Now we go to the first calculation question. Okay, they ask us to use the following facts for questions 2 to 7 because these are constants. So we just need to know what are these values. Okay, so I just want to highlight that this is mega. This is megajoules. That means it's actually 0.33 times 10 to the power of 6 joules per kg. But sometimes they do not just give you in joules per kg because joules per kg is a SI unit, right? It's SI unit. Sometimes they may give you in joules per gram. So you either change your joules per gram to joules per kg, which to me is more difficult because the kg and the grams are at the denominator. If not, you change your mass to grams, which I think will be easier. Okay, so you have to be very sensitive to what kind of numbers are given based on the units. So we have the first one is LF, second one is LV, third one 2100 is actually CI, this is actually CW. Okay, I hope you still remember what is your L and C. L is latent heat. We have latent heat of fusion, which is ice, which is from water, liquid state to solid or solid to liquid. Then we have vaporization, which is liquid to gas or gas to liquid. And after that, for C, it is the specific heat capacity. I purposely write my C small because it's specific. Of course, we have capital C, which is a heat capacity. Okay, so we have specific capacity of ice and water. Okay, let's start with the first question. A kettle with a 500 watts heating element, so this is my P, contains 1.5 kg, this is my mass, is left to boil, right? If the initial temperature was 20 degrees, how long does it take before the kettle dry up? This is the key point here. Dry up means when you open up the kettle, do you still see water? No, there's nothing inside, it's really dried up. That means initially I had liquid, it has turned all into gas. That means nothing left. So if I were to draw the heating curve, it will look like this. Okay, so if I draw this, right, what is this temperature? Will be 100. If I now were to open up this kettle, would I still see something inside? Will or wouldn't? Nothing. Will or will not? Yeah, you always like, then you see my facial expression, then you change. Will I still see something inside? What do I see? I will see not just water. I will see boiling water. I will see water boiling. The water boiling. Then now, at this point in time, I open up. Will I see something inside? Because I open up, all the steam will have escaped. I will see nothing. That means it has dried up already. So this is the part whereby it has dried up. So there are actually two stages. So if you were to draw this out, you wouldn't just stop here. Or you wouldn't just calculate this part. You would have calculated this part and also this part. Correct? So that's the meaning of dry it up. You must be able to interpret the situation. Okay? I will not go through the calculation. I'll just ask you, what do we use for this section? C or L? C or L? CW or CI? CW. Then over here, what do we use? L, F or LV? LV. Yes. My wife's favorite brand. Okay. So the heater has to provide all this thermal energy. That means it will be this part energy plus this part. So final answer, you should get 7610. Please do not write down the working. Do not just copy down the working. Just write down the final answer. Go back and try out. Can I move on? Any questions about this? Wilin, okay? Just write down the final answer. I will upload the answer, then you all can check. You need to be able to do this. That means you need to be able to draw your heating curve. Yeah, go to the next one. 10 kg block of ice has a temperature initial of -10 degrees Celsius. The block absorbs 4.11 megajoules. That means it's 4.11 times 10 to the power of 6 joules of energy into its internal store. What is the final temperature of the liquid water? How do I know that the ice has melted? From the question, how do I know that the ice has melted? Yes, they already prompted us that it's going to be liquid water. They want to know the final temperature. So, can we draw the heating curve? What was the initial temperature that we started off with? -10. So at -10, I give it some thermal energy. What will happen to this block of ice? Change state or change temperature? It will change temperature, right? So it will go up until when? 0 degrees. Then it will start melting. Correct? And will it change temperature again? May or may not. May or may not, right? Because at the end of this green color line, it has all changed into water at what temperature? 0 degrees. Okay, but maybe we will still increase in temperature. I don't know, because they want us to find the final temperature. Okay, so this is the unknown temperature. Let me call it X. So are you confident of being able to draw this heating curve? And so you must think, if I'm the ice at -10, what do I do first? Then when I reach my melting point, what am I going to do? Okay, basically very standard. Either you increase in temperature or you change it. So now for this part, do I use C or W? C or L? C. CI or CW? CI. Right? Because it is a solid water. How about the green part? LF. Fusion, right, is from solid to liquid. Then over here will be CW. You add this part, you add this part, you add this part, it must be equal to 4.11 times 10 to the power 6 joules. CI, what is CI? What does C stands for? Specific heat capacity. But we have three states. Can either be ice, solid state, or water, liquid state, or vapor, gaseous state. Okay? So you have to use the correct C. So the final answer will be 14.3. Just write this down. Just write this down. If you got it wrong, write this down. Go back, draw your own heating curve. Okay? Okay, question 4. 1 kg, 1.5 kg of boiling water. What does boiling water mean? 100 degrees Celsius. How do you know that the water is boiling? Yesterday we did the experiment, right? You see bubbles, you can assume that it is boiling water. So it is at 100 degrees. So the water is already 100 degrees. It was mixed with 0.5 kg of melting ice. So what does melting means? The temperature is already must be at 0 degrees. Now determine the resulting temperature. Who gives energy? Who takes in energy? And the amount must be equal. Right? I give, you take this amount. So now I need to draw two curves. One is heating curve. What am I drawing? Am I drawing for ice or water? Ice. When they start to make, when this is at 0 degrees, I give it some thermal energy. What will happen to it? It will start melting. It will start melting, right? It will not increase in temperature because 0 degrees is its initial temperature and it's going to melt now. So I give it thermal energy to help it melt. Once all the ice has melted, the temperature will increase, whereby it becomes water. So I'm going to call this X again. The temperature, the final temperature is going to be called X. How about for the boiling water? Flat or straight away go down? Flat, but boiling water, it goes down. It just goes down. It just goes down. Yesterday, did y'all catch the steam? Never, why? Y'all just let the water boil, right? So once I have this boiling water, straight away the temperature will decrease. We are not talking about steam at 100 degrees. If it's steam at 100 degrees, then it will be flat. It will change state first. Then after that, the temperature will decrease. I'm talking about boiling water. So at 100 degrees, it will start to drop and the resulting temperature will be X. So let me guide you once again. Over here, do I use C or L? C, W, C, I or C gas? C, W. If I were to give you, then you may have to give right in. Then how about this? The green part, the first flat part, it is LF or LV? LF. Then over here will be C what? CW. So you all know how to do this already? You repeat. Every time you read, you see this kind of question, you must determine what you are doing. Okay? How do I know all this? Okay, very good. Is this giving or taking in energy? Taking in. Can you calculate the amount of energy? This part can LF multiplied by the mass, right? This part, we started off from 0 degrees. At what temperature does it end off? What's the final result temperature? X. So X minus 0 is X. Multiplied by the C and the M, which is MC change in data, you get it in terms of X. Right? And their final resulting temperature must, for the boiling water, must also be X. Because they have reached this thing called thermal equilibrium. Then you equate them all. I give, you take. Is equal. If it's equal, what's the only unknown? X. Then we can solve. Go back, try. That was what I said like 5 weeks ago when I went through this. You must know what they are doing. I go to I see a determine the mass of ice at 0 degrees required to add to 0.3 kg of water at 50 degrees so that the final temperature of the water is 0 degrees. I want you all to draw the heating and cooling curve. Can you all try? None. This is for ice. Just a flat line. Why? Fine. Doesn't change what? For the ice, it doesn't change temperature. It changes state. That's why it became water at 0 degrees. How about the water at 50? That's all. So who is giving? Who is taking in? Water is giving. Ice is taking in. So here, do we use L or C? L, F or LV? Then this one, we use C, W. That's all. We don't even need to care about after that whether it freezes or not. It doesn't. Because we added just enough mass of ice to make sure that the final result is at 0 degrees. Can? Okay, I need you all to try the punch question. Can you all write this down so that you can go back and try? I know who has handed in and who has not. Okay, can you all do this? Question 6. You need to draw three heating and total 3 graph. Oh, okay, so this is the heating and cooling curve for ice and punch and cold. Okay, so I hope you have tried and you are able to get this. Okay, can? So actually not that difficult, right? Huh? Yes. Thank you for your words of affirmation that it's not that difficult. In the end, you'll get the answer of 2.41.
Oh my God.
Yeah. So you have to do it very systematically. No, it's not even physics Olympiad. It's a simple O-level question. So you just have to do it very systematically. Okay? Go back and try and see if you can work this out. You may also want to go back and try your TYS on this chapter. You'll find that the calculation is easier. Okay? Okay, the last calculation question. Again, can you try drawing the heating or cooling curve? But basically, this one should be simple, because if it's for water, it is just from 25 to 80 degrees. So you'll be using CW. Okay? So this is what the water is absorbing. It took in 462,000 joules of energy. But when I was marking, some of you made the mistake. There is energy that is transferred to the surrounding, 10,000 of it. So if you are the heat source, how much energy did you provide? You provided 462,000 plus that 10,000. You get it? Who absorbed 462,000? The water. But during that time, 10,000 joules was transferred to the surrounding. So what is the total amount that the heat source has to provide? You have to add them up together. So it will be 472,000. Okay? And this will actually come from the steam. But some of you miss out this part. The cooling curve. The steam actually undergoes this part. Then it drops to 80 degrees. So some of you actually miss out this part, which is your LV. So that's why your answer is very different. Your answer, like, don't know how many kg, 14 kg of steam. Okay, you all understand what is happening? the steam needs to condense first. Condense ready, then it will drop in temperature. Okay, I will upload the rest of the answer. So for those of you who have handled it, I made annotations why you don't really get the full answer. Okay, then the rest of you please refer to the mark scheme for this. But there's only this thing that I didn't have a chance to ask. 30 degrees water and 70 degrees water, are they the same state? Same, So if it's 30 degrees and 70 degrees, will they have the same PE? They have different PE. PE is potential energy. Same or different? Why? Why? Huh? What MGH? That one is gravitational potential energy. That one is when we refer to it as a big object. But molecular wise, we go to potential energy and kinetic